Okay, so let's learn how to draw Lewis structures for molecular compounds and polyatomic ions. This is one of those things that we do that there's actually different ways to approach it. And so if you have a different way of doing it that you learned in another class or from YouTube or something, and you can reliably come up with the correct Lewis structure, that's fine. You go ahead and do that. But this is the way I'm going to teach it. So there are steps in drawing a Lewis structure. First, you have to figure out the correct skeletal structure. That means that you have to figure out how the individual atoms are connected. Are they in one long line? Are they all clustered around a central atom? That kind of thing. Just helpful hints, hydrogen atoms are always terminal, meaning they're always on the outside of the molecule. They can only form one covalent bond. So you can't have a hydrogen in the middle with a bunch of different atoms around him. It's just not going to work. And then when you have to decide, well, does this one go on the inside or the outside? Generally, the more electronegative elements are going to be on the outside. And after we go through this section, we're going to learn about something called formal charge, which really helps us figure this out. Next, you need to figure out how many electrons you have to work with. How many dots are you going to have in your structure? So you're going to add up the number of valence electrons for each atom in the molecule. If you have an ion, you have to consider the charge on the ion. If it's a positive 2 ion, it got that way by losing 2 electrons. If it's, say, a negative 3 ion, it got that way by gaining 3 electrons, so you have to add or subtract those in. Yes?
But we only know the charge if it was given in the problem.
It would have to be given in the problem as, do this for the hydroxide ion. Well, then you know it has a -1 charge. Then you're going to put those electrons, distribute them among the atoms, and you try to make everybody happy. So hydrogen wants 2 electrons, everybody else wants 8 for the most part, and you try to spread them around. Sometimes you can do it, and everything works out great. Other times you come up short. When you come up short, that means that people need to share some more. And so we're going to have double bonds or triple bonds. So those are the instructions. Let's do some examples. Write the Lewis structure for carbon monoxide. So the first step is just to figure out how the elements are connected. Well, diatomic molecule, it's pretty simple. They must be connected to each other, right? So carbon and oxygen are going to be next to each other. And then we have to figure out how many valence electrons are in the molecule. So there's one carbon atom, and it has how many valence electrons? 4. Remember, number of valence electrons is the group number. And the oxygen has 6. So we have a total of 10 dots. Okay? You have to have at least a single bond connecting all the atoms, or they're not going to be connected. So the first thing I'm going to do is I'm going to put a single bond in there, and that's 2 electrons. And then I'm going to count as I draw in more dots. And I'm just, spreading them around, trying to make them kind of equal. So I've got 2, 4, 6, 8, 10. I'm out of electrons. Oh, yes. Are they happy? Nope. What can they do? Share some more. So what if this oxygen shared this lone pair in here? So let's do that. Let's take that lone pair off and make it a second bond. How are we doing now? We're better. Carbon's happy. 2, 4, 6, 8. Oxygen, not so much. So the carbon's going to have to pitch in too and take one of its lone pairs and share it. Now, this is not what occurs when a bond forms, you understand. This is how you think through what to do to draw the structure. And so now, carbon has 2, 4, 6, 8, and the oxygen has 8. Everybody's good. Usually when you start drawing your Lewis structure, it's going to be a little bit messy, and so you might want to just draw it neatly after you've figured it out. So we've got carbon and oxygen, and they each have a lone pair of electrons. And so here's our Lewis structure.
So the goal is to get it to a lone pair of electrons?
The goal is for each atom to have 8 electrons. So the bonding electrons count for each of them, and the lone pairs only count for the atom that they're on. Any questions?
You can write it either way, right? The one on the left or the one on the right?
Yeah, this is fine. You could put these lone pairs both on the top, both on the bottom, one on top, one on bottom, it doesn't matter. I kind of like symmetry, and so I tend to put them more symmetrically, but it doesn't really matter. Let's do H2CO. Well, the carbon and the oxygen are going to be next to each other. One of them is, well, you know, then we have to figure out where to put the hydrogens. Well, maybe we could put one on the carbon and one on the oxygen. That could happen. And then, so we'll try that. And then we have to count up electrons. So there's 2 hydrogens. They each have 1 valence electron, group 1A. There's 1 carbon. It has 4 valence electrons. It's in group 4A. There's 1 oxygen. It has 6 valence electrons. It's in group 6A. We have a total of 12 electrons. So now we set about making the atoms happy. So we need bonds, 2, 4, 6. Each bond is 2 electrons. Just the bond makes the hydrogens happy. They're very easily pleased. So I've got 6, 8, 10, 12. I'm short again. So we need to share some more. If I share one of oxygen's pair of electrons, oxygen's going to end up with too many. Because oxygen's good right now. It's got 8. Carbon is the one. Wait, that was backwards. If carbon shares, oxygen ends up with too many. Oxygen's good right now. So it's the happy one who needs to do the sharing. So we need to take a pair of electrons from the oxygen and share with the carbon. Carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8.
Then why is it 8 as opposed to 12? Like the original number that we needed.
12 is the total number of valence electrons we have in there right now.
Yeah, 12 is the total number of valence electrons for the whole molecule.
Okay.
And those are going to be shared around so that each atom, other than hydrogen, has 8. We can also do this more the way I showed you in the beginning, where you look at each of them with their individual electrons and figure out how to put them together. It's not necessary to do it this way. There is some significance in it, but if we do it this way, so here we see that the oxygen brings 6 and the carbon brings 4 and each of the hydrogens brings 1. This is going to predict that we're going to do these. And then the oxygen and the carbon aren't quite happy, and so they're going to say, well, I've got this one and you've got that one. Let's put those together and share them. And we end up with that. Is everybody happy in that molecule? Yeah. Could I have come to this conclusion doing it this way? I could have. It's just in how I decided to put them together. Can they both be right?
Yeah.
Maybe. Maybe not. Maybe one's better than the other one. How do we know? That's in the next section on formal charges. But for now, those are okay Lewis structures. Yes?
I remember there was a thing about like how many bonds it can make. So carbon can make 4 bonds.
Carbon likes to make 4 bonds. Oxygen likes to make 2 bonds. And so this is actually the correct one. Since you brought it up, let's talk about that. So oxygen has 6 valence electrons. And we draw it like that. How many unpaired dots does it have? 2. Oxygen usually forms 2 bonds. Let's look at carbon. How many valence electrons? 4. How many of those are not paired? 4. Carbon tends to form 4 bonds. Let's look at nitrogen. How many valence electrons? Cinco. 5. How many unpaired? 3. How many bonds does nitrogen like to make? 3.
How does that, so when you say like carbon likes to make 4 and oxygen 2, then what does that look like on?
Well, just knowing this, which is just a generality from the periodic table, that without knowing formal charges would help us to choose between these two.
Which is why it's the right one.
Yeah, this is actually the correct one, but what I've told you up until now, you have no basis to know that. Other than, I guess, the more electronegative element on the outside. So here's oxygen. Oxygen is more electronegative than carbon. And so that rule predicts that you'd want to put oxygen terminal on the outside, just only connected to one thing. But here carbon has 3 bonds, oxygen has 3 bonds. That's not ideal. Here oxygen has 2 bonds, carbon has 4 bonds. That's what they like to do. Okay? Any questions?
When we write the Lewis structure, why do we always put hydrogen on the outside?
Because hydrogen can only form 1 bond. So if we tried to do this, if we tried to do it like CHHO, that's not going to work. Because hydrogen can't make 2 bonds. So that's why hydrogen always ends up on the outside. When we say an element is terminal, we mean it's at the end. It's only connected to one other atom. So this just can't work. Any other questions? Let's do a polyatomic ion. Really simple one. Do you remember the name of this guy? Close to chloride. It's 1 less oxygen than chloride. Hypochlorite. So this is a hypochlorite ion. Yes, sodium hypochlorite is the active ingredient in bleach. So we've got chlorine and oxygen. There's no debate about how to connect them. There's only 2. They have to be connected to each other. How many electrons do we have to work with? Chlorine has 7. Oxygen has 6. And the -1 charge, we add 1. So we've got 14.
Will it always be an even number?
That's a good question. Will it always be an even number? We'll find out that there are some molecules that violate the octet rule because they have an odd number. If you have an odd number of electrons, there's no way that you can do the octet rule, because that's dependent on pairs. So we've got 1 single bond, that's the minimum. So that's 2 electrons, 4, 6, 8, 10, 12, 14. Oh, no need for multiple bonds on this one. It's an ion, so you need to put brackets around it and put the charge on the outside of the brackets. Now, mastering chemistry, I don't know why they haven't been able to do this, but it can't handle brackets on polyatomic ions. And so do not text me and ask me, how do I put the brackets on my Lewis structure? You just leave them off and just put the charge and it'll be okay.
So whenever it's symmetrical, it's done?
It's not necessarily symmetrical. The key is the 8. So chlorine has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. You're getting to 8.
Because you can have 1 on both outsides and it's still symmetrical, but it's not done.
Yeah, you can have different things that look unsymmetrical, but they're still 8. Question in the back?
I was going to compliment about, say thank you for the worksheets as opposed to Pearson, because I'm trying to make the Lewis structures on Pearson. Like, a lot of times, even though my cursor is right on the element, it'll like drop a carbon in there right next to it, and it'll be overlapping. And so I have to like reset it and then click down again. It's a lot slower than be able to drop at freehand.
Yeah, drawing definitely has its advantage. There are some times where doing something on a computer is just so tedious and so frustrating. And so, you know, when you do these types of problems on mastering chemistry, just expect to be frustrated, okay? And just don't But don't stress about it, okay? Because how much of the grade is 1 or 2 homework problems going to affect, right? If you get some parts wrong because of computer issues, it's really not going to have any impact on your overall course grade. So it's important to keep that in mind. The benefit of the online homework is the learning that occurs. And you enter in your answer and you immediately get feedback, yes, that's correct, no, that's incorrect. And even if I were Superman or Superwoman and could actually grade written homework for everybody, the problem is then, it takes a while to get it back, and by then you've lost interest. And the other option is, well, just assign problems where the answer's in the back. But then people look at the question, they look at the answer, and they say, oh yeah, I see how that works. Or some of these things, the details are so tiny that you look at your incorrect answer and you compare it to the correct answer and you don't notice the one little detail that's wrong. Mastering Chemistry notices. So yeah, there's frustration in the online homework.
The only thing I have with Master Chemistry is like, nope, that's wrong. It's like, well, I don't know where else to go with that.
But sometimes it does tell you.
Sometimes you have the pages and sometimes you have the page.
Yeah. And the other thing you have is me.
Yeah.
So you can text me, and some of you are real good about that. You text me like, why is this wrong? And I'm not going to hand you the answer because that's not beneficial to you. But I'll say, well, what about this? Or check that. Or I'll ask you a question to lead you into figuring out what's wrong. So take advantage of that. I sit at baseball games a lot. And I enjoy my knitting, but I enjoy answering questions too. Okay.